Hello, and welcome to the latest episode of the Gradient Podcast. I'm Andrey Kurenkov, your host, and today I'm excited to be interviewing Max Braun. Max Braun leads the AI and robotics software engineering team at Everyday Robots, a moonshot to create robots that can learn to help people in their everyday lives. Previously, he worked on building frontier technology products as an entrepreneur and later at Google and X. Max enjoys exploring the intersection of art, technology, and philosophy as a writer and designer. Quick correction up front. I say several times Everyday Robotics. That should be Everyday Robots. And my audio is a little sketchy in this one. Apologies. But I think you'll still enjoy the interview. And that being said, here we go.
So thank you so much for joining us for this interview, Max.
Awesome. Thank you so much for having me, Andrey. I've been a listener of the podcast, so it's really great to be here as well.
Oh, that's exciting. I don't think I've heard that before. So as usual, the way we like to start is just to hear about your origin story of how you first got into AI and robotics.
Sure. I think if we go back to the beginning, I went to school in Germany and I studied physics first in Heidelberg, and that seemed to really resonate with my interests about, science, technology, and sort of doing something deep and meaningful. And I was sort of on track to be a physicist and go into an academic career, maybe hopefully become a professor, maybe at some point in the end. And I was kind of doing that while I think I know that I was really into engineering and computer science in particular. And I was kind of lying to myself as I was doing physics. And this was in Germany before they had a pretty broad bachelor-master's thing. So if you got into right after high school, you were in that until PhD. And so it's not sort of an undergrad situation. But then I decided to switch, and I switched to computer science essentially.
Yeah. How far along was that in your physics studies?
I realized it pretty quickly, after one semester, and then I did another semester just to prove that I could do it. To be okay, it's not because it's too hard, Max.
Yeah.
It's because this is the right thing to do. And I missed all the cool part because then all my friends who I'm still in contact with, they all went all the way through to their PhD in physics, and they did a lot of cool stuff, which was way more interesting than the stuff you do in the first year. But I was happy that I switched and got a pretty solid, I think, computer science education in Koblenz, which is a small university. But I felt like the atmosphere there, and it gave me a lot of freedom to just explore and do the things I wanted to do. Because even and now we're starting to get sort of the curve to neural networks already when I was in Heidelberg doing physics. One of the things I did is on my little laptop, I wrote sort of a little neural network that used the webcam to do some image recognition. And this was pre, AlexNet revolution and all of that. So it was pretty primitive, but it kind of worked. You could hold up little objects. It was doing real time-ish, and it would recognize and classify them. So I already got the bug of ML and
just as a side project.
There's always that trend with some day job and a lot of different side projects.
Yeah,
but that was definitely something where it was quite primitive and not just something I hacked up on my computer, but it's kind of end to end in that this was also pre TensorFlow or PyTorch or whatever, and so I wrote the whole thing in Objective-C of all things at the time because it was on macOS, and that was fun though. And from that, I ended up in a research group and an AI research group in that university in Koblenz with Ulrich Vorbach, and they happened to also have a exchange with the university in Osaka in Japan, and I got lucky enough to get to go. So a few students got to go, and in our year, it was two of us. And we went to Osaka doing research there, and this was Professor Ishiguro's group. So, he makes these lifelike looking androids, and there were a bunch of other people doing.
Quite famously, I think a lot of people have seen them. Yeah.
Yeah, it's kind of crazy because it's a very specific approach to robotics, and they're doing way more in the teams I was working with too. But when you actually, you see videos of these android robots, they call them Geminoids, and you're like, okay, this is kind of so clearly uncanny valley. It kind of looks like people, but not. But when you're actually in the room with one of these, you really have this human presence feeling because, I don't know, because of all the things that come together. They have some actuation to move the chest up and down, and there's like subtle movements, and it really makes you feel like, even if you're not looking at it, if your back turned again, it kind of feels like a person.
Your brain is just hardwired to kind of believe it. Yeah.
So that was super cool to be sort of part of that area, and this is between University of Osaka and the ATR research facility in Kyoto. So we looking at research there, and my particular work at that time was mostly on simulation. Actually, we had this really interesting human-inspired robotic arm with artificial muscles, so these pneumatic muscles, and they didn't have a simulator for this. And if you take your simulator toolkit, maybe today they have it, but at the time there wasn't any primitive for something like that. So I created those that sort of sim to real system identification to have the force response of these things.
This was
these elements.
Around 2006-ish, or
when was this? Yeah, exactly, around that time. So 2006. I think I went back to Germany. This must have been 2007, 8, or something like that.
So it's kind of interesting now, a decade later, decade plus. Simulators are all the rage for robotic learning, but you got going on that kind of early.
Yeah, so I'm sure we're going to get into what we do with simulation today quite a bit later. But at the time, I was using ODE. If you remember that simulator framework. Today, we use Bullet mostly at work. But it was certainly, even a few years ago, you would still have people sort of talk about, should we do simulation of real robots? And I think it's about a good mix of both, and you can do a lot with simulation, certainly.
So as a product of that exchange program, I guess, how long were you in Osaka, and did you wind up just writing a full simulator?
I was there for actually not that long, a little over half a year, but it was quite the intense time because I was doing this research project, which was, writing a simulator, not rewriting a lot of the physics, but sort of combining this for the research we were doing. Honestly, it's so long time ago, I vaguely remember what we were actually using it for, which was some novel control method. I think it was sort of simulated annealing, inspired to do some control of that robotic arm. And I think I threw that stuff up on GitHub, and you can see a little video of like the most it could do, which was move the end effector, the hand to roughly an area, and then you're like, okay, great, it did that. So it was not super advanced at the time. But the other thing I did while I was there is that the two of us who went there, two students, actually started a little company, not in robotics at all, because we were just interested in what was happening in this whole Android, iPhone, smartphone space, which was starting to happen around that time. And we were just looking at, okay, now you have this little platform which has always on internet. It has motion sensors. It has a camera. It has OpenGL on it. And so we were kind of crafting a use case about making use of all these capabilities, and created this augmented reality mapping application, turned into a little company that was eventually acquired by Google. And that's how I ended up at Google in the first place. So this was around, I think ended up happening in 2007, 8 or so. And we quickly went back to finish up my master's because it was really close. And that made immigration easier, among other things. And then I started at Google in 2009, and it's been there ever since.
Yeah, no, that's a fun journey. You wound up getting into augmented reality also, quite a bit. Now it's huge. I think at that point it was just starting out. So, interesting. And so it seems to me that once you got to Google, you were sort of working on sort of, at least a few years in, you started working on very novel products similar to augmented reality that were early tech that were not developed. So what was your journey from joining Google to winding up at Everyday Robotics?
Of course, I think, the interesting thing is at that time, I still had that image in my head of an academic career and, at least to a PhD. And pretty quickly when I was at Google, I realized like, no, this is the place where things happen. This is where I want to be. And it so happened that I joined around the time when Google X became a thing. Like that started around that time. And I initially I was on a team that was doing mapping and sort of AR stuff. I worked on mobile maps.
And Google X is the sort of moonshot factory for kind of wild bets for people who don't know.
Exactly. Yeah. At the time, so for your listeners, this is where the self-driving car project started, which is now Waymo. And I think not just Waymo, but I think it really inspired the whole industry of self-driving car companies going after this, because they sort of saw that, okay, here's someone who's really going after this problem. After many years of research in that area, someone really trying to build a product. And I see what we're doing now actually somewhat similar, as there's been a lot of research in this field, and I think you really need to try to make it happen in the real world. And so that's really what Google X was about. I think in the founding of Google X, that was one part. You really want a moonshot project, meaning some huge problem that exists in the world, some radical solution to solve that problem, enabled by some breakthrough technology. And those three kind of always have to come together for Google, or what is now just called X projects under the Alphabet umbrella. And at the time, there's a lot there. And the initial project I worked on, which was one of the first that was pulled into this new Google X construct, was a visual search. So now you have Google Lens, which you may have used.
Google Lens just added search with text and images, so it's getting pretty exciting.
Exactly, and again, and sort of the theme as we discuss history here a little bit, we were working on that back then, and it was much more primitive. It was really quite good at some use cases and not quite so good in a general sense. So we were nailing, wine labels, but how often do you need to look up a wine label? And so now I think
pre-deep learning. Yeah,
exactly. It was all pre-deep learning. There were a couple of really dedicated, impressive pieces of infrastructure to do classification, annotation, and so on. And now, of course, ML since then has enabled a lot more use cases and capabilities. This ML revolution kind of happened between that.
Mm-hmm. So you started out working on this visual search, and then I think you, perhaps after that, wound up working on Google Glass. Is that right?
Yeah, that's right. I think, we were still working on visual search, and AR was still also part of this. AR in the sense that, when you use Google Lens today, you get this overlay over the camera image, and if you have a QR code, it tracks sort of on the image. That kind of AR. And I think what we realize today, which is a problem that isn't solved yet, is that holding the phone in front of your face is not the best interface for this kind of information. What you really want is this just to be there. And so we quickly got into wearables. And I think that is still a problem that has a lot of potential. And Google Glass was sort of a first attempt at really pushing for that and having a super lightweight version, tiny computer, little display that's always with you, and sort of really takes away the technology a little bit and gets out of the way.
Yeah, for anyone who doesn't know, Google Glass is wearable glasses, and there's a little screen up on the top right, roughly speaking. So there's an overlay, as you say, that displays information in your field of view, which is what augmented reality pretty much is.
Yeah, exactly. And there's a lot of interesting work happening since then. I feel like nobody has really cracked it yet, but a lot of people are a lot of companies are very seriously in that space and trying to solve that. So I think that's going to happen sooner or later in a way that is it's smoother in an experience than what we're able to do at the time. But then, Google X was also just like a very vibrant place. So this project was happening there, but also Google Brain, as it was called at the time, now just part of Google Research. This whole, can we actually do large scale deep neural networks? And I remember when, Jeff Dean and Andrew Ng were sort of presenting on like, hey, we found this cat neuron, if you remember that. Mm-hmm. And so it was a cool place to be at the time. And of course, the self-driving car project, and many other exciting things, balloons with the internet.
Yeah, some really pretty wild projects, some of which haven't panned out, some of which are in the process. I think Google Glass is still being applied in some settings. It's kind of fun for me as someone at Stanford to, I guess, just think about this academia industry connection that has been forming for a while. And especially for Google, like the self-driving efforts were to some extent launched by Sebastian Frun, who also worked at X, and then Andrew Ng famously worked with Google on starting Google Brain. So yeah, it's interesting, like you said, to try and make things in the real world. And some of these cutting edge, really, really challenging problems, it seems like, can sort of, there's been efforts to jump from academia to Google where you can actually try and make it real. So pretty cool.
Exactly. And, you mentioned Sebastian. I think that's an interesting case because we worked fairly closely together on a lot of these projects. Obviously, he initially, I think, had like a smaller scale sort of street view version outside, and then really made it work. The team at Google then really made it work at scale. And that's where the value is. You can do an experiment of having Stanford campus digitized, but has limited value. But if it's the whole world, like Street View today, it's really a game changer. I think similar with self-driving cars. You have it on a test track or in the desert. If you remember the DARPA Grand Challenge that Sebastian and others were working on, and then taking that to be into a project at Google, at X, and really trying to make it work as a product for people. And now we have cars driving people in Phoenix, Arizona, and in San Francisco. It's quite exciting.
Yeah. There's been an interesting kind of trend, or several cases where you have these really scrappy prototypes, like the DARPA Challenge, where a bunch of academic teams competed and basically hacked on top of different car platforms. And later in VR, the first Oculus was completely hacked together. But just these initial, I guess, examples that sort of show a vision and this might actually be possible, then led to these efforts that, billions of dollars, a lot of new technology, and tackling these really hard problems, which has been really interesting. So then you worked on Google Glass, and so you've taken a bit of a break from robotics since working on it in your master's. So how did you find your way back there? And were you sort of still thinking about it throughout this time?
It was always in the background because in the end, what I love working on is future technology in all its shapes and forms. And I think robotics is definitely up there. We all want to be, I think, living in a world where robots are way more present than they are today. And I think at the time, so I was working on Glass, and after that worked in Google search for a little bit, but then around, which is now 6 years, a little bit longer than that ago, this project that we're on now on robotics in X sort of started to be taking on a shape that's similar to its current one, sort of reshape things in within X, and that's around the time that I joined that. And it might be worth talking about why we're working on robots in general, and I think.
Maybe now, can you provide an overview of everyday robotics?
Of course, yeah. I think so. It comes back to this. This is about our future. The demographic changes across the globe are real. Societies are getting older. We're living longer, but we also don't want to be working longer. So there is this problem coming down the line. We have some time to solve it, but it's also a really difficult problem to solve. And I think robotics can really clearly help with that, and robotics is not helping with that today in the degree that it could. Meaning, robotics is being used fairly broadly in a lot of different use cases in factories, warehouses, and so on, but it's really not in these everyday spaces that you and I live in. It's not in offices and homes to the degree that it's really adding a ton of value, and and why is that? It's because there's this gap in capabilities, especially in these unstructured environments like homes and offices, these everyday spaces we live in. It's just a lot harder to do anything. Mm-hmm. It's one thing to weld a door for a car, which is kind of similar from one door to the next, and it's a completely different problem to pick up a cup, which is on a table, which might be configured completely differently every time you see it. So there's that fundamental problem. And that's something I don't have to explain probably to most of you listeners or anyone working in robotics, certainly that is just a huge challenge, these everyday tasks. And that's the sort of huge problem we're trying to solve.
Yeah, you're really doing a moonshot there of just solve this huge problem of enabling robots to basically work in household environments and achieve the dream of Rosie the robot that I think everyone is familiar with.
Yeah, and so we should talk a bit more about this, because in the end, I definitely want a robot at home. Definitely want one that's helping us with everything. I think there are a few steps along the way to get there. And, we're taking a very specific approach right now where we, just like self-driving cars said, we have to actually go, away from some roads, some test tracks to every street, sort of L4, L5 in the terms of these autonomy levels. We're saying we really have to go after unstructured environments. And there's sort of this sweet spot with offices where, we're already in them. But that helps to, if you build any product, it helps that you interact with it every day. Mm-hmm. And they're sort of in the sweet spot of complexity and accessibility. So we can add a lot of value in offices. There's a lot of different tasks that we can do today and that are actually useful. And we're building in order to achieve that, we're building our own general purpose robot. And, I think it's sometimes people get hung up on that general purpose terminology. And since you mentioned Rosie the robot, it's not an all purpose robot. I think we're not trying to go in that direction. But we are also very clear that's not a special purpose robot. And as we talk through the different tasks that we're doing, maybe we'll see that, pick one of those. Let's take a trash sorting, which is one of I think the first one we might have made public back in 2019, maybe, where we talked about this one task that our general purpose robots are doing, and that's going through offices, driving around, looking in the trash bins and fixing mistakes. Basically, if there is a bottle in the compost where it doesn't belong, or a compostable cup in the recycling, then it would look into that, grab that, and put it in the correct bin. And it actually has a big impact on sustainability, because what we've learned in sort of diving deep from a product point of view into this use case is that if there's one bottle, for example, in the compost, that whole bag now goes onto landfill. Because it's such a difficult problem to sort of sort that out. And you could say like, okay, let's solve this with robotics, and we build a special purpose robots. People are doing that, companies are doing that, and they build sort of trash sorting robots, and they're really good at that. They can sort that quickly, efficiently. But that is a big investment. It's not very flexible, and when it makes sense, then you should be using that. But imagine having a robot you have anyway, because it's, I don't know, wiping your tables already. You can quickly deploy it to this other task. I think you're suddenly in a completely different realm, quite similar to when we went from large dedicated mainframe computers to personal computers, and now mobile phones and so on, which have all these capabilities. They're sort of general purpose in that sense, rather than being specific to one task. So that's really core to how we're thinking about solving this problem.
Yeah, and this makes a lot of sense. You said we already are in offices all the time, and places like Google have a lot of offices, really large spaces with lots of people. So there's no shortage of things that robots could help out with. And to your point of unstructured environments, maybe we can kind of wind back and point out that in order to do unstructured environments and be generalizable, basically at the bedrock of that is machine learning and learning in general. And it's kind of interesting timing. Around 2015, 2016, deep learning started coming to robotics as well, a few years after AlexNet. So, yeah, maybe you can talk a bit more on what are the main approaches in terms of machine learning and AI that you are pursuing at Everyday Robotics. And we'll dive into papers later, but maybe just in general genres.
Of course. Yeah, I think the key idea or challenge is that no two situations that the robot is going to encounter are going to be exactly the same. So programming anything explicitly is not going to solve the problem very well. And so it has to be learned in some way, learned from data, learned from experience, and then also learned in a way where it generalizes across examples. And that's another description of machine learning. And so it makes a lot of sense. And for us to be betting on ML actually has sort of different flavors throughout the system. Some are at this point super established, where especially in perception, how else would you determine if something is a cup or not, right? That's like that wasn't the case, I think, when we started. If I think back at 2016, where a lot of the stuff was still fairly new. You would still sort of wonder, is this even the best way to solve that problem? Now we don't have that discussion anymore. Our perception system.
Now it's easy. Is this a cup or not? That's one of the things that AI is good at.
There's always challenges, especially if you want to get to a few nines in reliability. But it is clearly the way to solve this problem. And so our perception system, takes in different kinds of sensor data, RGB, depth from stereo, LiDAR, and then produces, object detection, bounding boxes, pixel-wise segmentation, for instance, or semantic segmentation, and tracking of people, other objects in 3D space, including their pose and so on. So all of these outputs of this ML system, because it is fundamentally an ML system, can then be used to build applications on top that solve specific problems. And that ML system is already one where we constantly feed back in new data. So imagine you have a robot. Right now we have robots. I mentioned the trash sorting example. We also have them wiping tables in cafes and cleaning. And every time they do that, that data gets reused as training data in the system. in many different ways, and I'm sure we'll touch on them over time. Some of them in simulation, some of them in sort of more supervised visual learning context, and we use that data and we train our models and they get better over time with that. So that's sort of a well-established part. There are other parts that are more out there, more in the
less clear
research.
How to do it.
Yeah,
still.
exactly.
Yeah.
And we also have a bunch of bets in that direction, and especially when it comes to sort of motion and enacting on the world, we take in part sort of a practical approach to this, where if you want to have a learned system where you move your robotic arm, for example, you can try to do it fully end to end. You get the raw sensor data in, and you take the raw, torque output into the pixels to torque. But in that scenario, you're putting a lot on your network. Like your network has to learn a lot of things, and so quite often we have different action spaces, different state spaces where they're sort of abstracted away from it. So, for example, your action space could be just Cartesian positions in 3D space, maybe even constrained, and then we use inverse kinematics to translate those into how the robot arm should move. And that is a sliding scale on both ends. On the input end, you could say, like, okay, I'm going to use pixels, or maybe I'm going to use processed depth information that already went through maybe another neural network whose job is just to produce a good depth image. And then we use that as an input to a more sophisticated, let's say, reinforcement learning framework. And I'm sure we'll get to talking about some of the stuff we've been doing there. But so that's kind of how we generally think about how machine learning plugs into robotics, as building a system that fundamentally gets better with more data and has sort of this flywheel running.
Yeah, that makes sense. We dream of, as you interact continuously, you learn from your mistakes, which at a high level is reinforcement learning, but in practice is pretty challenging. And you mentioned, all these sensors. So maybe to help out our listeners, can you describe the robotic platforms you work with? They're not, like Humanoid, whatever. So give us a bit of a picture.
Of course, yeah. And, the best thing is definitely go check out everydayrobots.com for some videos of our robots, the latest generation of them. We currently have about 100 of these, a fleet of 100 of these operating in our offices. And not just in our office, but in a bunch of different buildings. And the exciting part is that they're still prototypes. They're not a finished product, but they're getting quite sophisticated. So they're pretty sophisticated prototypes. And we can do certain things at something that you could start calling scale, like certainly if you compare it to an average robotics lab. And so this robot hardware, which we built, designed in-house, is a mold base with a one-armed mobile manipulator, which has a gripper at the end, so a two-finger system. It's also modular, so it can pick up or attach different tools. For example, for wiping tables, we attach sort of a squeegee tool, and that similar in tool use for people. We use that same principle, but for a lot of cases, this two-finger gripper actually works pretty well. We use that for the trash sorting use case and picking up random objects.
Yeah, that's still what is usually done in research, just two fingers.
And I think there are clear limitations with all of this. Having one arm is a limitation, having just two fingers is a limitation. For us, it's sort of the challenge of finding that sweet spot where you have enough capability from your hardware, but you don't have so much choice that it gets intractable and that there's so much complexity that you can't handle it. So this is kind of how we ended up with the current morphology and the current system that we have. There's quite a bit of compute on board. We do a lot of ML inference, of course, in real time. as we process the sensor data. And we also do quite a bit of it in the cloud. So the robots are cloud connected. And they do mapping, navigation, and then a lot of these manipulation use cases. The two that I already mentioned that we talked about is trash sorting is one example, wiping tables, cleaning in general, opening doors is another, which is obviously important if you want to navigate an office building. And then we also do many, many more tasks at a sort of experimental, smaller scale. But I think it's really important that tasks that count to me are the ones that we run in daily operations. The ones that are solving a real problem, something that someone wants to have done in the office, and they're doing it continuously every day. That's really where I think we can sort of make a difference and have like a real impact, as opposed to just adding another experiment where you show you can do it once, which is important as a first step, but then that's not sort of the moonshot to crack.
And do you already have this robots continuously operating in your offices?
We have robots operating every day. Yeah, that's a really important part for us to, get in the habit of operating them, getting to cycles of trying things out, getting feedback, also generating training data, and using that to make the robots better over time. And so we exercise them in that way. We have robots running every day. Simulation, of course, is another big part in which we scale that to a whole different level. Every robot that you operate comes with some overhead. It's a physical thing in the world. Gears might break, or the real world is difficult. Hardware is hard. So we do that, but whatever we can do there, we can do many, many more times in simulation. So that's a very, very important part of our bet as well.
Mm-hmm. Yeah, it's around 6 months ago, there was this news of the robots getting out and cleaning up in these kitchen spaces. And I remember that quite well. At the time, the notion that you already had robots operating not just in the lab, but in, actual real world settings where other people are, for the listeners, maybe this doesn't seem that crazy that you have robots just moving around and cleaning up cafeterias. But this is rarely done, really, just about anywhere. So it's really quite significant.
Yeah, I think we're really quite lucky to be able to do that. And I do think that is one of the puzzle pieces that is needed to solve this problem and to really make something that works. Is, self-driving cars, you have to get them on the road and drive them. Robots, you have to get them into everyday spaces and have them perform tasks every day.
Yeah. And so, this news came out 6 months ago, but by that point, this project has been going, 5-6 years. So clearly it took some effort. And maybe we can rewind and just go through on the research end, on the technical end, kind of how that progressed and how these individual challenges all built up to this being possible.
Yeah.
So maybe as a start, it's an interesting mix of research and building a product. So how, as a group, what is your process to do that?
Right. It depends on which part of the problem we're trying to solve. Traditionally, we're working in this area where a lot of the problems we're having to solve are research problems, but we're not a research team. Mm-hmm. We work really closely with the research team at Google, especially Robotics at Google, who are a research team in capital R research. Mm-hmm. And they publish papers and they really move the field forward. We partner with them really closely, so closely that a lot of the times the papers that are published have joint authorship between our team and the team over at Google. And we do that in the areas from our end that make most sense in, moving us closer to our vision of having robots in everyday spaces and having them perform really well. And a lot of this is, well, it comes in different forms. Just like earlier when I was describing our sort of ML system, it comes in the form of working with a team over at Google that works on depth imaging, learned depth. We would work with them, which might be coming from an application that is more about augmented reality, actually, coming back to that, where you really need that to sort of infer the scene. And we work with them on that. But then the bulk of the collaboration is on with Vincent Van Hoek's group at Google, Robotics at Google, to do learning with robotics in a sort of more end-to-end sense. So some of the work we've done there goes back to, let's say, at least 2015, whereas this project in its current form kind of existed since 2016. And the work that happened then was, okay, we have a much more simpler robot at the time, which was just a robotic arm. You might remember this. Some of your listeners might remember this. So there were a row of robotic arms doing bin picking, a bunch of objects in a bin in front of them. And what the robots would see with a fixed camera, I think at the time, looking at the bin, RGB, no depth, as far as I can remember. And then the action would be, it changed over time, but the one I sort of remember working at some point was a constrained Cartesian end effector pose and maybe a signal to open and close the gripper.
And so just saying, move by 10 centimeters down or left or right or whatever, right?
Yeah. Actually, I don't remember if it was relative like you described or if it was absolute, but you get the point. There's some sort of position in space that is done there. And I think if you go quite further back, there was sort of a supervised version of learning that, which had these rows of robots, which we started calling robot schools. Today we're calling them robot schools, where the robots just keep learning over and over, and we generate data that way. I think there were like 8 robots, maybe. And that at the time, I think, was already considered pretty large scale. We've been able to take that much further since then, but that was an important step to get more data into this problem of learned robotics. Because if you remember, the ImageNet revolution, or really all the ML revolution was partly due to ImageNet, which sort of gave you some scale on the data, and you could work on it. And that's one of the fundamental problems in robotics, is that you can't just easily have a data set like that. It's a bit more complicated. And so with these early approaches, you would get to bin picking success rates between like 60 and 80% or something like that. And that is cool, especially because it's a new approach, but it's not practical. If you actually wanted to do bin picking, that's not enough to solve real world problems. And so the next approach then was this research on QT-opt and reinforcement learning based grasping, which suddenly things got quite interesting. Because in the same setup, at the time, I think we were doing it with these KUKA arms, so still sort of arms bolted to a table, picking from bin in front of them based on RGB inputs. And they were able to run this at a fairly, high enough closed loop control that you would look at it and see this emergent behavior of, okay, it's sort of pushing stuff aside and then, singling out individual objects and picking them up. And you would just look at that and see like, okay, there's something really interesting happening here. We've just taken robotics from something that is robotic to something that feels much more organic. And at that time, we on our project sort of really said like, okay, we want to really invest in this much more deeply and turn that into a capability. And this is in the end what if there are other research projects we should talk about, but if I quickly sort of span the arc from that really early one to something we have now, the trash sorting that we do have is based on this fundamental principle. It is a a learned capability that is used from reinforcement learning in the real world and in simulation at massive scale, where just through data and success failure annotations, the robot has learned the skill to solve that problem. And I think that's really fascinating as a capability. It's a very different way to think about robotics, solving robotics in that sense, versus solving in the sense of I'm going to sit down and tell the robot exactly how to do what and when. So that's been very exciting. And that's one of the research projects back then that really inspired us to get a lot deeper into machine learning, not just for perception, but for motion as well.
Mm. Yeah, this is a really key thing about robotics. You can't have this sort of like you just scrape a bunch of images and you get an image net. You at some point need to run the robots and collect the data. And at that point, you basically must use reinforcement learning of, you mess up and you figure out why and you get better. And so, yeah, jumping back to Qt-opt, when you were starting with this bin picking problem, and basically the robots started out not knowing how to do it, and then they, failed to grasp a bunch of stuff, and then eventually they were quite good. So maybe you can describe a bit more on, how that whole setup was, how much data you wound up collecting, and just kind of what you ended up having.
Yeah, I think for the amount of data, I'll have to look at my cheat notes here. But I think in the original project, so the setup for these original arms was, ended up collecting around, I think, almost 1 million graphs, maybe like 800,000 or something like that. And it took something like this takes months. So I think a couple of months in this case, using 6 to 14 robots at the time. And I think we over time got more efficient, but the fundamental problem is still that you do need a lot of data. And especially this is still true with reinforcement learning today, that it is quite data hungry. And so if you want to learn a skill from starting from noise, so if your policy starts with noise and really has to learn everything just from trial and error, that requires a lot of data. And I think there are two areas that we could maybe talk a little bit more deeply about to help solve that problem. One of them is simulation, and in particular about how do you lower the sim to real gap? How do you leverage simulation in a way where the simulator is really close to the real world performance? Because otherwise you end up with something that works really well in simulation, but the moment you try to run it on the real robot, it doesn't work. So you have to solve the sim to real problem. And we've done some really interesting work there, especially with GANs, that I think is super exciting. And the second way to address it is with learning from demonstration, which is less data hungry in some ways. So we're doing that too. Some of the tasks we're operating today are based on reinforcement learning, and some of them are based on learning from demonstration. We're also investing sort of bringing those together because we kind of want the best of both worlds. And it's much easier to bootstrap something from either human demonstrations or from scripted actions, which is often where we start. But human demonstrations have the advantage that they come with a very positive labeled example. This is one way in which you could do it that we think works well.
Yeah. So we're going to go ahead and jump into some of this more recent work. Beyond Qt-opt, going into simulation and imitation learning. Just as an FYI, if listeners are interested about this initial project, Sergey Levine was in a prior episode and shared a lot of fun details. So you could check that out. So jumping forward, I think, as you said, you moved beyond just pure RL to working on some of these new directions. And I think in particular, one of the more exciting projects wound up being BCZ, which is zero-shot task generalization robotic imitation learning. And this is notable because you're using imitation learning, and also because now you're not just doing bin picking, you're actually moving to generalizing. So it was let's chat a bit about that project and how it, let's say, interacts with what you're working on right now.
Yeah, BCC is super exciting. And you had Eric Yang on the podcast too, who is the lead author on that one. And I don't remember, was that before the publication or after? So I think he would know a lot more of the details. But I can give you like the rough idea, which is that to make it more concrete with a specific task. So let's say you have in this setup also a robot. It's standing with a desk in front of it, which has random objects on it. And so the task is, we're moving way past sort of bin picking here. The task is, much broader. You might want to say, okay, move this object from here over there, or take this banana and put it in the green bowl. And these are the kind of tasks you might want to do. So it's getting way more open-ended. And in order to achieve this, we this is done with our robots, and a lot of this work is I work from research robotics at Google and our team, and they used behavior cloning fundamentally to bootstrap from human demonstrations in this environment to a learned policy that is language conditioned. So breaking that down a little bit more, you would have something like a person, many people directly operating the robot with what we happen to use, this Oculus controller. You can imagine it, they have this VR controller, and it is sort of tied to the robot's end effector. And when you move it, then the robot's end effector moves just like that, and you can press a button to open and close the gripper. And you can imagine how that is a fairly intuitive interface to let the robot arm do something useful, and then you have some other buttons to move the robot's base if you need that as well. And so you use that remote control interface to have the robot perform different tasks, and then you label those tasks. If you put the banana into a bowl, then you just write in English language, put a banana in a bowl. And with that, you create this fairly rich data set that allows you to train this language conditioned neural network. So at that time, I think for this paper, they use a fairly basic sentence embedding model, actually. And we should talk about LLMs later and like the whole revolution
we'll get
that's coming down there. But even with very simple sentence embedding models, you can now create something where you just tell the robot to a instruction that is in the holdout set, or that the robot hasn't seen before. Let's say you've taught it what it means to move something into a bowl, but you've never told it to move that particular object into that particular bowl. And it's able to interpret the training data and transfer that into a successful action. But again, that early work, forget the exact success rates, but we're still like in sort of the 60+% success rate. So this is quite early work, but it is super promising because I think language really opens up a whole new area of, really an API for the robot, an API for robot actions that is way broader than a very narrow control interface. It's much more relatable for people because we already speak languages. And this is where we sort of get to the magic of language models, and we should talk about the SayCan work later, is there seems to be like way more relevant information encoded into these language models that we can then even use for tasks like long horizon planning. And I think that's just super fascinating as well.
Definitely, yeah. Language combined robotics has been gaining a lot of ground, and SayCan just came out, so we're going to chat about it for sure. Just to add real quick, if you're interested in BCZ, there's a really fun blog post, Can Robots Follow Instructions for New Tasks? We'll have links to this and other stuff in the description, and you can just Google it and see the Everyday Robotics robot doing a whole bunch of fun, varied tasks, and there were like 100 different tasks, so quite impressive already. And then, maybe to jump on the other train that you mentioned, which is simulation, and combining simulation with reality to be able to do it. And you had several projects while working on the sim-to-real gap and learning to grasp for this sorting, I think, for the trash sorting project. So, can you describe sort of what has been achieved at Everyday Robotics with simulation and learning for robotics?
Yeah, of course. So with simulation, today we use it for a number of really very different use cases. One is that we're probably focused on the most for now is ML training in different shapes and sizes. We also use it for testing, for software development, for hardware development, because what you get is a virtual robot, one that you can pretty easily wish into existence and multiply by 1,000, and one that you don't have to worry about doing anything you don't want to do. So there's just that flexibility in using simulation for a lot of these things. Especially on the machine learning part, we use it, for example, to bootstrap a lot of these reinforcement learning policies. So imagine let's go back to that trash sorting task. Let's say you're doing that. What we would often do is we would start the training in simulation. So there would be a simulated setup with the full robot and the scene, say sort of a 3 bins in front of it, and randomized objects that we put in there. And then we just go crazy and, really with thousands of robots, generate a lot of data and bootstrap a policy that way. And the important part is that is still only in simulation. So in the end, what you want is a robot that works in the real world. So you could just train something in simulation and then run exactly that policy on the real robot. That sometimes, surprisingly, actually works, but most of the time it doesn't work quite as well. Maybe it works a little bit, but the metrics aren't quite there. And so what we would often do is you do that, and up to some point, and then you start training with real world data, and that allows you to get to higher success rates. But the same thing is still true, where the better your simulation, the closer your simulation is to real world, the more you can bootstrap, the faster you can bootstrap. And so solving the sim to real problem, the reality gap problem, is still very important. And we do this in a number of different ways. I think one important approach is that we're not writing sort of physics simulator from scratch. We currently use mostly Bullet, use others as well. But then we combine that. We modify Bullet as well. We've added some certain things there over time. And we really use that and other tools to shape the simulator to the specific robot we have. So it's not sort of that the everyday robot simulator is very specific to the robots we have on the team. And that allows us to really shrink this reality gap, because we can fine tune it to the specific hardware we have, the specific use cases we have, and honestly, to fine tune the performance of it, which is good. There's a lot of computation that needs to happen if you simulate all the physics and the whole world, and you have to render the camera views and all of that. And so we do that and create a lot more high quality data.
Yeah, and this sim to real gap is in large part because we can't simulate things perfectly, right? So the physics are a bit off, especially when you're trying to grasp objects. That contact is really tricky to get right. And then, yeah, you can't render something with computer graphics to look just like in the real world. So if you train just in simulation, your data isn't the same data as in the real world. And as you said, having a better simulator is certainly part of how you can do that. And it's interesting that you have one. And then, yeah, maybe, aside from that, what sorts of things do you do for, let's say, the image component?
Yeah, that's where it gets, I think, super exciting, where we use we use GANs to create better fake sensor data, essentially. So in particular, when you're simulating camera images, what you would typically do is you have some sort of 3D renderer, and you take your virtual world with the environment, the objects, the robot itself, and render that onto a camera frame that looks like the kind of camera image you would get on your robot. And then you have a choice. You could sort of throw a lot of compute. You could do ray tracing and get like a super high quality image. It takes a lot of resources. You could also do lower fidelity rendering, and that actually gets you surprisingly far, because a lot of these networks don't really seem to care that much about the fidelity. They're able to extract relevant information somehow and look over the fact that you have jagged edges and the colors aren't quite right and your illumination is too uniform. But then as you try to get into realms where you really want to get to high quality, it starts to matter. And so what we do is we've experimented with a number of different generative adversarial networks to translate simulated images into real-world images, and the other way around. We also had some in the past to sort of create something that's neither real nor simulated, sort of a canonical one. But I think the most promising ones are those that in the end translate a simulated image into a real one, and then just present that translated real image to the robot in simulation. And that really, really boosts success rates on these tasks that you're training. And I think the papers and research that was published in that area, I think the two worth mentioning here is first RL CycleGAN and then RetinaGAN. I think RL CycleGAN is interesting because it's based on the CycleGAN idea. So you have a network. It's a funny thing. I think the best way to explain GANs is always with this. You draw this one image with all the boxes. We're in a podcast, so I'm going to try my best to do that in words. But essentially, you have two domains. You have the simulated images. You have the real world images, and you train a neural network that translates one into the other. But you do it both ways, because then you can add an additional loss that compares translating a real image into a simulated one into a real image that should be very close. And now you have a loss. And you can do that twice.
That's a cycle, right?
Exactly. And that's a cycle. And you could do that twice, depending on which one you start with. And so now you're getting a bunch of different losses that you can add onto your network and optimize for, and do your thing, do your gradient descent, and get something that ends up being pretty close to this data, sort of pixel-wise translation. And the idea with RL CycleGAN was like, what if we do that, but we do it sort of task specific? So let's say we have a reinforcement learning task, let's say trash sorting, and we formulate a loss on top of that is actually related to how well you're doing at your task. So did you pick up an object correctly? Did you, whatever your reward function is within that RL task, that becomes one loss, meaning the GAN network learns to translate simulated images into real images in a way that preserves those details that matter for the RL policy. And at the same time, it doesn't care so much about those details that don't matter to the policy at all. And that really makes a difference. So that was a really, really promising work at first. It has one big downside, which is that it is quite task specific. That's the whole idea. You sort of add that RL loss in there. And so the next one we did was written again. And what you do there is you have a cycle consistency loss. It's also a cycle again, but then you add this perception consistency loss. You basically say you run something like object detection with RetinaNet, hence the name. You do some object detection on the original image and then on the translated image, and then you compare your where your bounding boxes are and if they which classes they assign, and then now you have another loss. You can say what I want to optimize for here is that if I can detect objects well in one image, I should be able to detect them pretty much exactly as well in the other image. And that works really well. And the advantage for that of that is that you can use it task agnostically. You can use that same thing for one task or for another. It's not tied to a specific RL loss. And so we've been using that a lot. And I should say with all of this research work, this is always in collaboration with research at Google, robotics at Google.
Yeah. So it sounds like I would presume to do some of the stuff that you're doing continuously, especially with trash sorting, this research is already deployed in practice, and you probably learn in simulation to some extent, and also use this sim to real approaches to be able to deploy it. Is that right?
Yeah, absolutely. I think when we do take a task like trash sorting, and that is learned with reinforcement learning, that is how we deploy that, and in our real use cases and in our real environments, we deploy that policy. Not everything our robots do works this way. We have a lot of tasks which are sort of done the more traditional way, where you program the robot more explicitly. But as soon as something works, we we really use it.
Yeah, and this is really exciting because it's one thing to demonstrate something in a lab and another thing to actually deploy it. And really, there's not been too many use cases of RL getting out into the real world robotics. So it's always cool to see.
Yeah.
And then, now jumping forward to the most recent work, which is really exciting, SayCan. I think it just was announced a couple of weeks ago. And as you said, this is connected to this other trend in AI of language models. So things like GPT-3 that basically, in some sense, understand language. They can parse sentences and understand jokes and a lot of these kinds of things. And, language, one of the issues, it's not grounded. It doesn't see the world. It doesn't move around. But there have been ways to connect it to robotics, or starting to be ways. So maybe you can let listeners know pretty much what SayCan is and how it works.
Yeah. So let's set the scene first. The environment that this work in the SayCan paper operates is a, we have these kitchens at work. So there's like tables and objects, and you have a robot, one of our robots in that environment, and now you want it to do something, but you don't want to be very explicit about having to tell it, okay, first drive over here, then raise your arm, then reach your arm out. So you don't want to be explicitly controlling it that way. Wouldn't it be great if you could just tell it in a very high level natural language command what to do, or even better, just describe your problem, and it figures out the steps that it needs to get somewhere. And so what SayCan paper does is that it says, okay, let's assume the robot has a bunch of atomic capabilities. Let's say it knows what picking an object in front of it means. It knows how to drive to a certain spot. If you tell it drive there, then it can do that. So we sort of abstract that away. We say, however that is done, as long as we have a value function associated with it, we can use it in this framework. So value function here is assigning a value to the current state with respect to the goal. So my current state, let's simplify the state, is just the RGB image of what the robot sees right now. And as long as you have something that can assign how likely it is to get from this state to your goal, then you can use that task. So that's one part. The other part is how do you get to your eventual goal from where you are right now? And so one of my favorite examples in that paper is, I think the phrase is just something like, "I spilled my can of Coke. Can you help me throw it away?" And so you ask a large language model to rate different phrases that describe these atomic actions with respect to which one of those would be most useful to do right now in order to get to my end goal. And then you combine that with the value function of what my current state is. And through this combination, you can rank all the different atomic actions that you could do in this very moment. And then you just repeat that. You ask the language model, what should I be doing in this state? You ask your value function if this is in the right direction, basically. And what happens is, just by saying something like, "Oh, I spilled my can of Coke. Can you help me with that?" The robot ends up saying, "Okay, that means I'm going to drive over there. I'm going to pick up the can. I'm going to drive to the trash can. I'm going to put it in the trash can. I'm going to drive over there to pick a sponge, take that sponge over to you, and start wiping." So that's kind of mind blowing to me. Again, this is kind of this is still early work in that direction, but it shows a couple of really important things. I think one, it shows that large language models are able to do long horizon planning. Like, they're somehow inherent in that structure. You're able to decompose tasks into their subtasks. And the other thing is that it was so funny. This was announced just a couple of weeks ago, but in that same week, there was a bunch of other large language model news. Like, in the same week, DALL-E 2 was announced, right? And also the Palm, new very large language model from Google. And so all the trends there are still pointing pretty straight upwards. So the capabilities of large language models are still getting bigger. And even, I think, in the SayCan work, the model that was used isn't even like the most sophisticated one yet. I think you probably wouldn't have seen a big difference because we're still only looking at a bunch of different atomic tasks. But imagine the tasks you can do are sort of, in the hundreds and the thousands. Then you're going to start to really leverage the capabilities of these very large language models.
Yeah, exactly. And it's quite interesting because in robotics, one of the key challenges is you're solving, a lot of things. You're solving perception, you're solving movement, just, touching objects, picking up objects. And then one of the even harder challenges is just planning, as you said, which is just decision making. Like, how do you do the thing you're supposed to do? And at that point, if you really want to generalize, you basically need some form of common sense, right? Like, us humans can figure out, okay, this is what I would want to do now. But this is, common sense is a pretty high level of intelligence. And so, yeah, it's really exciting to see that maybe language models trained purely on text can have some of this common sense. And then in SayCan, you show how you can connect it to a robot that knows how to look in front of it and know what's possible and not possible, and sort of, take what the language model spits out and tune it to also match the image and the real world. And and now you can do like over 100 tasks, right? Mm-hmm. I think in your paper, all of us around this kitchen doing like 10, 12 steps, which is a huge leap for anyone who doesn't do robotics from what has been the case.
Mm. Yeah, it's super exciting.
Yeah. So, yeah, we got to pretty much, a few weeks ago. So that's a summary. I guess maybe jumping back from the research, I don't know if you can reveal too much, but, what is the current hope or current objective for what your robots can do in the offices? So they can help out in cafeteria and sort trash. What do you think might be possible, in terms of number of tasks and maybe new types of tasks?
Yeah, I think in the end, so we're operating a couple of different tasks related to cleaning and inspection in offices today. We're still also building out a lot of fundamentals. For example, a capability like being able to open doors. It's a pretty good bet that you're just going to need that if you navigate in the office or in your home.
Mm-hmm.
So there's a lot of that fundamental work happening. When it comes to how many or which specific tasks, I think first of all, like counting tasks has a little bit of this fractal coastline problem.
Yeah.
Right, because depending on how you count it, it's orders of magnitude more or less. But the main point that I would say is to sidestep that is, what do we need the robot to do? What actually delivers value to someone who's to the people in the office or eventually in homes? And we've identified some of these cases, some of which we've talked today. We're going to be identifying others. We're going to be changing that over time. I think we're really building something here that is a business and that ends up solving real world problems. And we're going to do that. We are already doing that based on machine learning in a lot of different ways.
Yeah. Okay. Yeah. So basically solve the problems that need solving and really pushing the boundaries of what's possible using some of this research in collaboration with Google Research and Google Robotics. Yeah. So I know as a robotics researcher, when some of these details came out, I was really impressed and looking forward to seeing what you can do. And just to wrap up, I think, really interesting to talk about everyday robotics, but we can switch tracks a bit and just talk about some of your other interests.
Sure.
If anybody Googles your name, it's actually really interesting to go on your site and see that on top of everyday robotics, you have all these other projects. So yeah, what are the other things you like to explore?
Yeah, I should say these are all small projects. Like, at my day job, I do things that need large teams and solve really hard problems. These smaller projects are a little bit my escape to actually write some code and build some hardware and software end to end, and being able to sort of own the whole project.
Just something that's not a moonshot.
That's something that's not a moonshot, and something that I can do over a weekend or something like that. And I've done little devices around the home and things like that. Maybe the one project that's most relevant for this audience too is a recent one around which actually involved large language models. I'd been playing around with philosophy and large language models. Actually, I have two projects on that. One which I haven't published yet, and another one which I have, which is called Wittgenstein 2022. And so the idea was, okay, Ludwig Wittgenstein, the philosopher, wrote this one work, the Tractatus, and has all these philosophical phrases in there which have a very distinctive character. And I was like, could I use GPT-3 to just write more of those? And it was interesting because it's not, at first I started playing with the GPT-3 playground, the OpenAI playground, and you can put some text in, but it's a whole book. And so I ended up using the fine-tuning API that they have to fine-tune GPT-3 on this whole book and then produce new sentences. And it's kind of funny because you start to explore the limitations of these large language models. You see the capability, which is style-wise on text and down to spelling, it's really spot on. But then sort of conceptually, like logically, there are often like complete contradictions, obvious contradictions, and things that are just plain wrong. I have a tendency to believe that that's actually going to change as we scale these large language models. And there, especially in the Palm research that came out recently, there's sort of interesting analysis to that end. You mentioned the explaining jokes one, right? Sort of that's a capability that previous generations wouldn't have been able to. And while that isn't like super critical, I think it points in the right direction. And so, on this project, I made a little website where if you go to Wittgenstein.app, you can get your generate new phrases, and it's kind of like a art project, fun side project. I actually made this late last year, partly when I caught COVID. I was stuck at home, and finally did this. I had this idea in my mind for a while.
Yeah. So we'll link to that. Check it out if you want to read some AI generated philosophy.
Exactly.
Wittgenstein is an interesting one to read.
Yeah.
So that might be a lot of fun.
Yeah, and it gets pretty deep pretty quickly too, because you start to think about, okay, what is meaning even? When I'm reading Wittgenstein, I do a lot of interpretation of these phrases, and I try to think what he like meant by it. Mm-hmm. And you're noticing like, well, I'm putting that same work into trying to interpret these character sequences that GPT-3 contributes on. So who's actually like, how much work am I doing as a reader of this anyway? How much work is it? So it's all really fun and games. I'm not a philosopher, and I'm
sure a philosopher could write an essay about the implications of this project in terms of Wittgenstein's philosophy, which is connected to language.
And that exactly, it's very self-referential.
Yeah, so it's cool to see there are some just projects for fun and not, solving some big world problem.
Yeah.
Alrighty, well, I think we'll finish up with that. That was a really fun interview, really interesting to me. So thank you again, Max, for taking the time.
Cool. Thank you so much. It was really great being here.
And just to do our usual outro, again, this is the Gradient Podcast. It is associated with thegradient.pub, a magazine where we publish articles by AI researchers and just people in the AI space. If you enjoyed the interview, as always, you can put a review on Apple or share it or just listen to it twice, whatever you feel like. So thank you for listening, and be sure to tune in to our future interviews.